Good evening. My name is Julie Burns, and I'm a senior biology student here at Lycoming College. And I'm very excited to be introducing tonight's guest speaker. But I'd first like to start by thanking our sponsors for the event. They are Lycoming Center for Energy in the Future, which takes an interdisciplinary approach to studying how we use our energy and the effects this will bring in the coming years, as well as our outdoor leadership and education program, which helps to develop leadership skills and learning beyond the traditional walls of the classroom. Our Sustainability Committee, which is a student-led organization dedicated to bringing sustainable initiatives to campus. And finally, our Clean Water Institute, where research students help to expand our knowledge and restore the waterways along the West Branch of the Susquehanna River. So our guest speaker tonight is the Evan Pugh Professor of Geosciences and Associate of the Earth and Environmental Systems Institute at Penn State University. He has served on many advisory panels, such as the National Research Council's panel on abrupt climate change and the United Nations Intergovernmental Panel on Climate Change. He was the co-recipient of the 2007 Nobel Peace Prize and has written numerous papers and books, one of which was chosen as Science Book of the Year by Phi Beta Kappa in 2001. Currently, he teaches and conducts research on climatic records and flow behavior of large ice sheets in order to predict changes to sea levels and climate in the future. So please join me in welcoming Dr. Richard Alley.
Thank you. Oh, dear. Oh, what a pleasure. Thank you. Thank you. It is really fun. I have had a day. I got up at 6 this morning and got a fleet services car and drove over here, and we've been going since 8. And I've been to a bunch of classes. This is a fantastic place. And the students and the faculty are really doing wonderful things, and it is an honor and a privilege to be here. If you're sitting way back in the back corner and you have trouble seeing the screen, the slides are over here, and there are seats up front. So if you have trouble seeing, come on over, and we're friendly. We don't bite. So I'm going to take you on a tour. I'm going to start off, so that's an iceberg. And I wanted to thank Barb Eldred at the Dean's office, who has arranged all of this stuff, and she jumped through a lot of hoops. And thank you for coming out tonight. And I'm going to scare you a little bit, I think, before I get to the good news. And I'm going to do the scaring with penguins to make it look a little better. So these are pictures I took in Antarctica at some time or another. So we're going to use penguins to smooth it off. And I'm going to walk you through a few points. And this first one I probably shouldn't have to do, but I'm going to do it anyway because we need to carry this out of here to other people, how fantastically useful science is. Then I'm going to walk through how we really get help from energy. And we owe a lot to fossil fuels. But it's going to end. We have to do something else, and the sooner we get started on doing something else, the better we are. So that's where we're going in the course of today. So we'll see what we can do to this, okay? So, like I say, I don't think I would have needed this, but I suspect that now I do. That it is worthful remembering that science works, that medicines do cure diseases, that people take computers and they design new airplanes, and then they build them, and then they take them out on the runway and they fly. And, you know, this is something else. And, you know, I have my cell phone in my pocket. You probably have one too. And it is, think about it for a minute. How would you make a cell phone? Right, it's a little bit of sand for the glass and the silicon, and it's a little bit of oil or some organic material for the plastic, and it's the right rocks, the ones with the rare earth elements and the gold and the copper, and science and engineering. And I've got Einstein in my pocket, right? The GPS uses relativity, it uses special and general relativity, and if we didn't understand relativity, it wouldn't work. And it uses quantum mechanics in the computer. When I was a student, be perfectly honest, we thought relativity and quantum were the craziest things in the world. You've got them in your pocket. And if you didn't have them in your pocket, you wouldn't have a cell phone. And be very clear, if you took the sand and the oil and the rocks and you took them down to the Senate and you gave them to the senators and said, please turn this into a cell phone, the monkeys would type Shakespeare before we'd have a cell phone. Right? But science put it in your pocket, and it really does work. And science does advance. You'll meet the Galileo people. Galileo changed somebody's mind, and then people didn't like Galileo, so you scientists will change your mind, and we don't have to worry about global warming because you always change your mind. No, we don't. Right? It is true that for little things, we needed quantum mechanics and that Newton wasn't right. And it is true for really big, fast things, we needed relativity and that Newton wasn't right. We needed Einstein and Bohr. But when I model a glacier, I don't write a quantum wave function and I don't use a relativistic calculation, I use Newton. And the useful parts of science, the big things, I don't think we've ever thrown one away. At the point we have something that works, when we get new discoveries, they build on it. They don't overturn it. Science works and it builds, and I think that's really important to know, okay? Now, this is the energy group. We're talking energy. I'm going to lean on energy a lot here. I don't know exactly the wattage of that bulb, but it's probably 100 watts. The wattage of me is 100 watts. I put out if you could collect the energy coming off of me right now, I'm about one light bulb. And you're one light bulb, and you're one light bulb, and you're one light bulb. We get that by burning food, and our food use is about 2,000 calories per person per day. I ate the moose at dinner, and I may be over 2,000. But at any rate, 2,000 calories a day is 100 watts burning day and night. But you know, I ride my bicycle at home a lot, but I took a car over here. And the moose was refrigerated, and I didn't refrigerate it, and I'm not riding a bicycle to power the light. And if you take all the energy that is used to take care of me, and you put it in these units, it's a little over 200,000 calories a day. What I can do is 2,000. What is done for me is 200,000. What is done for you is 200,000, and what is done for you is 200,000. And it's 80-some% fossil fuel. And it does the transportation and the heating and the cooling and the plowing, and we love it. Be very, very clear. It's fantastic, and we don't want to give this up for anything. When I came over this morning, I drove by the iron furnace. I come from the town of State College. The town of State College is a suburb of Penn State. When Penn State was founded, there was no State College. It grew up to serve the university. Penn State was founded up the hill from the iron furnace. And when the iron furnace was working, it would have looked like this. This is Hopewell furnace in a diagram from the Park Service, but it was turning red dirt and limestone flux into the iron that built the East. And the power to make that rock melt came from charcoal. And the charcoal came from trees. And it came from lots of trees. And if you did this very long, it did that to the landscape. A furnace in blast, and the people taking care of it took the trees from about a square mile a year. And then they had to wait 30, 40, 50 years for more trees to grow back. So a furnace, when it was running, a square mile of trees a year. Now, if you go to a gazetteer of Pennsylvania, go to the map and say, in Pennsylvania, where do we remember the name furnace? All of the ones on the left there are furnaces, and there's a whole bunch more that aren't on that list. And every one of those in blast is a square mile of trees a year. Now, the ones on the right are forges. You took the pig iron and you forged it into useful things, Valley Forge, and another square mile of trees a year. That and a whole bunch more did that. We are in Penn's Woods. We are in Pennsylvania. When the first European settlers came here, they said that a squirrel could go up a tree on the Atlantic coast and stay in the trees to the Mississippi. The first forester of the Commonwealth was Rothrock, and Rothrock wrote about the Pennsylvania desert. Now, it wasn't a desert, it still rained, but we didn't have trees. We have 1 million deer in Pennsylvania, they were essentially gone. We have elk in Pennsylvania because we re-imported them from the Rocky Mountains, they were gone. I'm a Nittany lion, there's no Nittany lions, there wasn't a deer to eat, and there wasn't a tree to do it behind. Basically, if it was bigger than a rabbit or a squirrel, we chased it out of the Commonwealth. And we didn't let the trees grow back until the 1900s. Now, if you've ever tried to read by firelight or by candlelight, it's not very easy. And so what did we do for lamps? And the poor people used to use a biofuel called camphene. It burned clean. It was alcohol and turpentine, but it was sort of explosive. And there are horrible old stories in the newspapers of people burning themselves to death. And the rich people burned whales. So you send Yankee whalers out to scour the world oceans and to find whales and to cook them, and then to bring back the oil, and then you can burn them. And this is the history of whale oil production in the Yankee fleet. The date is 1800 on your left, it's 1880 on the right. You can see peak whale oil in the middle there. This is a complicated story. There's a civil war in there. The fleet is crushed in the sea ice off of Alaska, and the insurance rates go through the roof. But what is the fleet doing in the sea ice off of Alaska? There's no whales that they can catch closer to home. They'd cleaned the ocean of what they could catch. Now, if you watch above, there's a blue line there, and that is the price of whale oil. As the whalers got good, they drove the price down, and it got down to what would today be $7 a gallon. And then it started going up. And when they hit the halfway point, it goes up to about $25 a gallon. And then there's a green line. They went up the road here, and they said, wow, oil leaks out of the ground. If oil leaks out of the ground, maybe there's oil in the ground. And they drilled the first modern oil well. Now, that history, 100 years of whaling, at the peak, there were 10,000 sailors out of New England looking for whales. And it collected about the equivalent of 11 hours of US oil use today. Right? So the idea that when we run out of petroleum, we go back to what we did before is ludicrous. But it's very clear that we let the trees and whales grow back after this. And they knew this way back. So if you haven't seen this before, there's a fantastic thing. This is an editorial cartoon. It was published in the magazine Vanity Fair in the year 1861. So it's right before the Civil War. And if you can't read the bottom, it says it is the grand ball given by the whales in honor of the discovery of the oil wells in Pennsylvania. And it's oil's well that ends well. The oil wells of our native land, may they never secede. We wail no more for our blubber. Right? We have trees and whales because of fossil fuels. And it's really that simple. And so it's fantastic. But when we quit burning whales and trees, they grew back in 100 years. We're burning fossil fuels about 1 million times faster than nature saved them for us. And the time to grow back another batch is 100 million years, not 100. And so it really, you may people who talk about choosing between fossil fuels and renewables. There's no such choice. We can burn and then we can learn, or we can learn while we burn, but there's no other option. Because the fossil fuels, whether they get through decades or a couple of centuries, they will run out. Now, this is where we come to global warming and the scary parts aside from that. And how much fossil fuel we are given by fossil fuel companies is flabbergasting. The coal miners are filling trains with coal, and it's stuff. And the frackers are filling pipelines with gas, and it's stuff. And the oil people are filling pipelines and tankers with oil, and it's stuff. And when you burn it, it makes CO2, but it's still stuff. We don't see it. It's hard to visualize. If you took the gas from my car and all the other cars and you liquefied the CO2 and put it on the roads, it would be an inch deep every year. In 10 years, we'd have no joggers in America. We'd all be cross-country skiers, you know. And you know what trash looks like. I drove by the trash dump down there. In America, we put out at the curb for the trash collector a half a ton of trash per person per year. I'm responsible on average for a half a ton of trash. I'm responsible for 19 tons of CO2. Think of all the trash trucks, think of all the trash you've ever taken out, think of all the trash dumps, half a ton per person per year. CO2, 19. Okay? And this will change the climate. And this rests on a four-legged stool of understanding, with each leg being a whole bunch of supports that is really solid. Right, so, and I'm going to walk you through the stool briefly, the physics, the models, the data, and the history. So we'll see what we can do with these, okay? So we'll start with physics. We knew before Einstein, before quantum mechanics, we knew that CO2 was a greenhouse gas and it would cause warming. The first serious computation of the global warming from fossil fuel CO2 is made by Arrhenius in the year 1896. He's a Swede. Okay? If you've heard the tweet that global warming was invented by the Chinese to destroy the American economy, if they planted Arrhenius in Sweden in 1896, my hat is off. Okay? This is physics. It is real. It cannot go away. The modern understanding, a lot of it rests on Air Force work right after World War II. And the Air Force was not doing global warming. They were doing heat-seeking missiles and other applications. If you are the Air Force, your job in part is to keep enemies from bombing your cities. The enemy has a bomber. The bomber has an engine. The engine emits infrared. You can follow the spot of the infrared, fly up their tailpipe, and blow up, and they don't get to your city. Except if you put the wrong sensor on, CO2 absorbs the energy. The molecules wiggle, they collide with other molecules in the air, they warm the atmosphere, and rather than seeing a target, you see a faint glow with the whole atmosphere warmed a little. Today it was cold, but even so, the sun warmed the Earth sent infrared back to space, and a CO2 molecule doesn't care whether the infrared is coming from the hot exhaust of the enemy bomber or from the sun-warmed Earth. The CO2 molecule absorbs the energy, and it warms the atmosphere with it. And there's a lot more energy going up from the sun-warmed Earth than coming down from enemy bombers. And so if you look down from space, on the right, lower right there's a little plot, and that's what a satellite sees when it looks down at different wavelengths. And that purple divot there is energy that is not getting to space because CO2 absorbed it. And if there were more CO2 in the air, it would absorb more. The observation, it's fact. You just observe it. This is physics. We're putting 19 tons of CO2 per person in the year into the atmosphere, and it absorbs energy and warms the air with it. And so it's basic. We know of absolutely no possible way to release CO2 to the air and not have a warming influence. It must warm. It's physics. Now, If we want to make that useful, what do? We solve the equations of science for cases that we care about. And you know, F equals ma. But when it came time to build this building, you actually have to apply that to real things to find out how strong the beams have to be so the roof doesn't cave in. And we as scientists do this. You could call this engineering or applied science or a lot of different things, but you solve the equations for cases we care about. And when I started doing this, we did it with slide rules and log tables. I lived through computer punch cards. Now we call them computer models, but we're all doing the same thing. We're solving the situation for something we care about. And a model, like my wife's penguin here, is not the real world, but they're useful. They help us to do things. They help us to understand things. They help us predict the real world. And people really do get on airplanes that were designed on a computer and fly through the air on those airplanes while they tweet that we scientists don't know what we're talking about. So I have never in my entire life seen a global warming model. What I have seen is people who build representations of the Earth in their computer. And they put in the physics, PV equals NERT and F equals MA and conservation, and then they put in the Earth. How much sun we're getting and how, where the land is, where the oceans are, how fast the Earth rotates, and a whole bunch of other things like that. And then you turn it on, and what comes out is Earth's climate. And it has Gulf Streams, and it has El Niños, and it has prevailing westerlies. And those models that are used to study the climate are now also used to predict the weather. And a lot of the groups are using the same model for weather as they are for climate now, because it works. And nobody goes and puts global warming into the model. What they do is put the Earth into the model, and global warming falls out. And there's just, this one, if we had more time, I'd do movies for you. This is a simulation of the Earth's climate. The land is dark, and the ocean is colorful. And it has El Niños and La Niñas and Gulf Streams, and nobody went and said, please make an El Niño. They said, follow the physics, and that comes out, and it works. And if you tried to make such a model, but you told it CO2 doesn't warm, what happens? The Earth freezes over into a snowball. No one has made a vaguely accurate Earth model while not including the radiative effects of CO2. Nor can you explain Venus, nor can you explain Mars, nor can you explain the history of the Earth, a whole bunch of things. You implement the physics, you get warming from CO2. It has to happen. Okay? Now, this is an interesting set. If you're in the back, this may work better. On the top is a projection, a prediction that was made with an early model in 1989 of how the world would warm. And on the bottom is what the world actually did. And more warming in the north, more warming on land, less in the Southern Ocean was projected in 1989. It's a fairly coarse resolution model, so it doesn't look identical. But what happened is what was projected. This is a different view. It's actually going north to south and through the year. So it turns out the biggest warming is in the Arctic in the winter. And on the left is what was predicted by the model, and on the right is what would happen, is what happened. These models are not just explaining things, they are predicting things, and they are predicting things successfully. This works. Okay. Now, it is warming. I showed you a little bit of it there. There's lots more. How do we know it's warming? Well, we have thermometers. We have thermometers analyzed by NOAA, by NASA, by the British group, by the Japanese, by the Berkeley group with their private money. If you just throw away every thermometer in the city and just look at the country, they show warming. If you do thermometers in the ground is warming. If you do thermometers in the ocean is warming. If you do thermometers taking up balloons, they show warming. Thermometers looking down from satellite, they show warming. If you were caught in the blizzard, it snowed here. When it's really cold, you make it warmer, there's more moisture in the air, it may snow more. But if you look at snow and ice that care about temperature the most, we have less river ice than we used to. We have less lake ice than we used to. We have less seasonal snow cover. We have less seasonally frozen ground. We have less perennially frozen ground. We have smaller glaciers. We have shrinking ice sheets. We have loss of sea ice. All of the big pieces of snow and ice that care about temperature are shrinking. If you ask plants and animals where they live and when they do things during the year, the vast majority of the shifts are in the direction of warming. And so we have this interwoven fabric of evidence that all says the same thing. This happens to be today. This is an anomaly map for the world, and oranges are above average and blues are below average. And if you're close enough, you can look over there and see that you're a little chilly. But if you were really close, you'd look at the bottom, and it says that the world is above average, the northern hemisphere is above average, the southern hemisphere is above average, the Arctic is way above average, the tropics are above average, and the Antarctic is above average. We still have weather, but it is getting warmer. Here's the data again. 1880 is on the left, and 2016 is in the upper right up there. So this is the data showing warming. This is the NASA version. Like I say, there are other versions. If I just zoom in on the right, this is a whole bunch of different versions of the temperature history. There actually was a hearing in Congress recently about the fact that the red line and the green line are different on there because NOAA tweaked it a little bit. And there was sort of noise about something wrong with tweaking. You can't see the red line from the green line, from the blue line, from the yellow line. Those are all different versions of the temperature history, but what do you see? They all show warming. And they show very, very similar with different techniques for analyzing it. But what you also see, I hope, is that there's some wiggles on the way up. We have El Niños and La Niñas that make it colder and warmer. We have volcanoes that block the sun or don't. And then we have CO2 that goes up and up and up. And so suppose, just suppose, that you had a job which was to confuse people about this curve, to get them to think that it's not warming. What would you do, aside from quit your job and go do something else? But there are people who work on this. And so suppose that you were out there trying to say that warming isn't really happening, right? And this is an amazing story, to be perfectly honest. But temperature does go up and up and up from CO2 and up and down from other things. I walked into a senator's office after the IPCC reports came out, and the senator said, "Would you quit lying to us? Global warming stopped in 1998. There's no warming." I had an alum that I had lunch with. We chatted a little bit, and later this person tried to get me fired. And in part, it was because global warming stopped and I was lying about it. Back in 2011, I searched on Google on global warming stopped in 1998. It came up with 155,000 hits. The first one I've quoted up there, there's a problem with global warming. It stopped in 1998. We should worry about ice ages. This idea that there's no warming was very widespread, and it showed up in the highest levels of government, and it showed up very broadly across the nation with people, right? But there's 1998, and what do you notice? Global warming didn't stop. But let me show you how it's done, because you're going to see this again, and you might as well know what's being done, right? So these are the same data, exactly the same data, but I'm going to break them out in chunks for you. So I was born in 1957. That's me when I was fairly young. And what will you notice is after I was born, it was getting colder. Right? I married my dear wife, Cindy, in 1980. We are still happily married. And you'll notice that we had to do something to stay warm because after we got married, it was getting colder. Right? We've been at Penn State since 1988. When I got to Penn State, it was cooling just a little bit. Cindy and I did succeed in staying warm. We have 2 wonderful daughters. And we took the kids out west in 1997, and you can see it was getting colder after we went out west to see the big parks. And bizarre as it may seem, there actually is a little glacier in Antarctica named after me. And in 2002, when they named it, it was the start of a very short, sharp cooling trend. And daughter Janet went to Penn State. She's now a middle school or science teacher, but when she went to Penn State, it was the start of a cooling trend. I can take those data and show you cooling, cooling, cooling. It's obvious that, well, see what I did? And remember now, we're up there. But do this. Go back here and draw a line and draw a box around it and blow it up and throw away the line. And look, there's no global warming. He's lying to you. There's no global warming. It's obvious. And your senators are making law based on that when that's what's going on. And it never ends, right? People have been tweeting this out from congressional offices that global warming stopped again. Okay? And what's you need to know, and you really do need to know this, anything that I can tell you of the solid science has an alternate version like this. Everything I could tell you, somebody has spun up an alternate version. And global warming stopped is one of them, but it's not the only one. And no, it didn't. But a lot of good people have been confused by this stuff. And you have friends and neighbors and relatives who are good people, but who have been misled by something that looks convincing even though it's wrong. And sort of getting the right information is a challenge. Okay? I told you there's a 4-legged stool. This is the 4th leg, which is climate history. I teach this class. We had a chat about this today in one of the classes. It was really fun. This is the last 400 million years of Earth's climate. 400 million years ago on the left, today on the right. Nature really has changed CO2 on its own, and that green band in the bottom is the changes in CO2. The blue is ice. And when there was high CO2, there was no ice. When there was low CO2, there was ice. And we know the direction of the arrow. It takes some more science that I'm not showing you there, but high CO2 melts ice and low CO2 doesn't. And we could change CO2 as much as the biggest things that nature did, but we could do it way faster. We really could be a geological force, but faster than geology did. And nature did change CO2, and that changed the climate, and that changed plants and animals, and it caused extinctions and migrations, and we could do as much as nature did, but a lot faster. Okay? So, what does it mean? Let me walk you through a little more scary stuff, and then I'll get to the good stuff. So, if we don't restrain CO2 emissions, the coming changes are bigger than what's happened already. The past changes had some winners and some losers. In the future, as the changes get bigger, it's mostly losers. The costs go up faster than temperature. A degree of warming, we're used to variability. 2 degrees of warming starts to hurt. We're committed to about that. But you start to get to the point we don't have any crops that know how to grow in it, and now that gets hard. So let me show you a few things. Things you would worry about are things like heat stress, sea level rise, loss of defense against invasive diseases, and a bunch of other things. So let's walk through a couple here. Upper left up there is India, not much air conditioning. Colder is on the left, warmer is on the right, and that is death rate, how many people are dying. And when it gets really hot, hotter than people expected, it puts heat stress on them, and a lot of them die. Lower right is US data. This is whether the temperature is warmer or colder than expected. Warmer is on your right. And that's the rate of rape. When do rapes happen in the US on warm nights? Anomalously warm. Okay. Lower right is when do people swear at each other on social media? Is that important? I don't know, but they do it on hot nights. Upper left is suppose you're in high school and you're taking the SAT and you went to scholarship, you're taking the Regents exam, and you have to take it in a hot day, and your school doesn't have air conditioning. That's test scores. And you'll notice on the hot days, it slopes down. On the hot days, when you're sticking to the test and you're miserable and you're sweating and you're ticked off that you're here, the scores are bad and you don't get the scholarship. Okay. This is 3 different measures looking at the tropics of when people shoot at each other or have civil wars or so on, against 3 different measures of temperature, but what you'll see broadly is the same in all of them. Changing the climate, you get what you don't expect, people don't like it. And when they get hot, they really don't like it. And so you tend to have civil strife in the tropics in hot anomalies. People shoot each other. Okay? This one came out a year and a half ago in the Proceedings National Academy. I'm going to blow it up for you so you can see it. Syria is not a happy place. Syria was not a happy place before, and then a drought hit. Some of the neighboring countries came through the drought, but Syria didn't. It was the straw that broke the camel's back that led to, civil war and migrant crises and a whole bunch of other things. We made that drought more likely with pretty high confidence. One of the robust things that comes out of global warming is that you dry out the subtropical dry zones, which is where that is. And so we loaded the dice to come up drought. It came up drought, and that country didn't handle it well. This is a projection. If we don't change the energy system, by the time our students are old, what happens to drought? Green is less drought. Siberia, Upper Canada, and Alaska, less drought. Not a lot of people live there. Everything else, yellow and red and purple, is more drought. A lot of people live there. And if we zoom in on Syria, where drought is already causing troubles, what do we get? More drought. So our military leaders have looked at this. And this will be hard for you to read from the back, but they have traced the dotted line that leads from climate change to drought to Syria, climate change to drought and heat to the uprisings in North Africa. They're very clear. They say, don't blame the civil war on climate change. It didn't cause it. It added stressors to a really stressed place. And eventually you go over the tipping point for the society and you get this. And our military leaders have actually been quite clear. They eventually get called to bail everything out. And if we make it work, they're going to have more job, and that's not a job they want. And so they look at climate change as a national security threat. It's a food threat. These plots are how growth of crops change as temperature changes. And when it gets colder, crops don't grow quite as well. When it gets warmer, they grow a lot worse. And most of our crops are grown pretty close to the optimum, but you'll notice all of those things plunging off to the right. When it gets warm, the crop yield goes. And this, the red areas, if we don't change our ways, by the time our students are old, more than 90% confidence that the average summer will be hotter than the hottest summer ever seen. You're making the average go outside of the envelope of what anything's seen in a world where heat already stresses our food. This is losing ability to work outside. You don't practice football outside in Alabama in August, you do it in the gym. You don't work outside at 3 in the afternoon in Phoenix in July when you're doing road repair, you do it some other time. And so that little green line at the top is we lose a little bit of the ability to work outside because it's too hot. That plunge down to the right is if we don't change what we're doing. By the time our students are old, the world could lose 40% of the ability to work outside safely in the hot month. Some countries, that'll be closer to 100%. If you're counting on tilling your field and you're not rich enough for an air-conditioned tractor, you might not be able to do it. And by late in this century, you start to have places on Earth where it is projected to be too hot to survive outside. It's like being locked in a hot car in the summer without an air conditioning. It's too hot, you die. And we could see that coming by late in this century in a few places and then spreading in the next century. Sea level is rising. Hurricane Gustav did not get into New Orleans. I would not have liked to have been that police person. But in fact, this case, the water stayed below the levee, but we're raising it. And at some point, it goes over the levee. This one is an estimate. What does warming do to the economy overall? And blue up there in Siberia and Canada is you could have a bigger economy in a warmer world. Pink is you have a smaller economy. Red is you have a lot smaller economy. It's not bad for everyone, everywhere, for everything. But what you'll notice is most of the world and most of the world's people are in the economy gets hurt. This one, red, is who is changing the climate? Who's emitting the most CO2? And blue is not much. And below it is who gets hurt when it gets hot. This is sort of that economy map again, and red is hurt a lot, and blue is not hurt much. And so red on top changes the climate. Red on the bottom hurts from the changing climate. And if you look at those maps and you believe in the golden rule, you may wonder about it. And Pope Francis said, you know, I looked at these maps and I believe in the golden rule. We can't leave this to our grandkids. Okay. Now, suppose that we take this and we say, what can we do with it? Are we doomed? Do we have an answer? Is there a way forward? And you know the answer. There's fantastic ways forward. Okay, so what do we do then? We will run out of fossil fuel as an economic resource. We won't run out of wind and sun. And we have this history of burning things till we run out, hitting a crisis and trying to find something else to burn. We know how to farm energy in a way that will sustain everyone essentially forever. Okay? We could become energy rich across the world in not that long. Okay, so remember my 2,000 calories per person per day. Where does it come from? Orange on top is where we grow crops. Green on the bottom is where animals eat grass on the range, and then we eat the animal. So we have changed everything in color on that map to feed us. Suppose, just suppose, that we decided that we want to build a solar farm that will supply all the energy that everyone in the world uses and enough extra for some growth. And just suppose that for now I'm going to put it in the Sahara on that lower one. Not because you'll ever build the whole thing in the Sahara, but because I want you to be able to see it. There it is. And if you're in the back, you're sitting there saying, wait a minute, where is it? Now that is a huge number of solar cells. Don't kid anybody. It'd be 30 years. But we've changed everything else in color on there to feed us. We could power humanity with a solar farm as big as that pink square. Now you're going to put it over the parking lot out here, so the car parks under it and you just plug in. But that's the scale. Okay. Now, this is also interesting. In the US now, there are a lot more people installing solar than mining coal. The scholarship tends to say that dealing with this wiser gives us more jobs, not fewer. You lose some. Fossil fuels make some good jobs, but you end up with more based on the available scholarship. Okay. One more, and then we'll call it a day here. Abe Lincoln, you know, he's the only president who had a patent for his own invention. He's on the stump saying we need inventors, we need patents, we need learning, we need wind power. He said the wind is one of the is an untamed and unharnessed force, and one of the greatest discoveries will be the taming and harnessing of it. So we went down to Texas when we made our TV shows, and they filmed wind farms. And the ranchers have put 5% of the ranch into turbines, and then 95% is in cattle and other things. And the turbines pay a lot better. They call it mailbox money. You go out to the mailbox and you get money out of it. And something like $5,000 per turbine per year, you don't get that for the cattle underneath. And so these ranchers sort of believe in this. If we built a wind farm on the windy parts of the plains and deserts of the world, it is about 5 times human energy use. Doesn't have to be in your backyard. It doesn't have to be in the water. Just the windy parts of the plains and deserts of the world is far more energy than we use. You just overcrop it over stuff like this. It's a lot of wind turbines. It's 30 years, but it's there. Okay. The opportunities that we could become energy rich, that we could become sustainable, that we could double what we use now or triple without that big a footprint, with much smaller environmental impacts. And that done wisely, done carefully, you improve the economy. And you look at the golden rule, and you improve national security, and you get more jobs. And the opportunities, we have spent millennia trying to get energy. And our ancestors did wonderful things, but they caused big problems. And they ran out of whales, and they ran out of trees, and now we have fossil fuels, but we'll run out of them too. But we now are the first generation that can look at each other honestly and say, we know how to fix this in a way that will last for a long time. And so I'll leave you with a picture I took in Greenland of an iceberg and a rainbow. Can we have a world with icebergs and rainbows? Yes, we can. Thank you. So I believe we have plenty of time for questions. And my understanding is that there are good people out here with microphones, and that if you wave, they will come running to you, and you can ask your question. And they may have to help me because that thing is in my eyes, and I may have trouble seeing who's waving. But please, let's go, okay? What do you want to talk about? So one right down in front here I can see. So if we'll start down here, and then we'll see if we can move back and around. But thank you for starting us. Yes.
This morning on my computer, I got an announcement that a new study showing a correlation between rising average temperatures, air temperatures, and diabetes was in place. And then there's a whole discussion about why that's happening. But you can add that to your list.
Yes. There's a recent report from a number of medical groups representing something like, I think, close to half of the doctors in America that say basically climate change is a health risk. And they didn't have much on this one, but they did on heat stress. We lose a line of defense against a number of subtropical, tropical diseases. We get a lot more spread of ticks and other things. There's a tendency in a high CO2 world, the plants grow really well with CO2, but they dilute the protein and your food might not be quite as nutritious. And so these medical groups said this is a huge health issue now as well as in the future. And they said the best thing to do about it is to start getting off of CO2 and move to renewables. So thank you, yes. Yes, okay. We've got some over here, I think, whoever has the microphone. Yes, please. Okay. I think you're good.
Okay. Should we be concerned with release into the atmosphere from poorly drilled natural gas wells, from CAFO operations and the like?
Yeah, so should we be concerned about methane? If you're living near it, breathing the methane itself is probably not a huge deal. We're used to methane. We release methane when we have the wrong peppers for dinner. And so that by itself, there may be other issues, but that by itself is not a big one. The global warming potential, per molecule, methane does more than CO2, but in 10 years, the methane hits an oxygen and it changes to CO2. And so if we are really trying to hold down warming, methane is a big, important one, and we should get on it. If we're trying to keep the planet habitable in the tropics for people outside, methane is CO2 in 10 years, worry about CO2. So you'll hear people within the community arguing about how much we should worry about methane, and a lot of it has to do with whether they think we're really going to meet 2 degrees and we want to get to 1.5, and then methane's big. But if they're trying to keep it from going to 5, it's all CO2, don't worry about methane. So how much to worry about? Methane is easier in some sense than CO2 because once you fix methane, in 10 years it's gone. And the CO2, once we raise the concentration in the atmosphere, will be up for thousands of years. Okay. Yes, I'm sorry. Oh, yeah.
Hi, Professor. Thank you very much for coming tonight. If you could please talk for a moment about the benefits and any potential drawbacks of imposing a national carbon tax to accelerate the process of our conversion to renewable resources.
Yes. Okay. So I am not an economist. I am not a policy wonk. I'm a geologist. But I have had the opportunity to serve on committees with some really good economists. And the economists to whom I've spoken, who are serious about this, love a carbon tax. And let me walk through this for all of you. We did this with the students today, but you know that we tax tobacco in the United States, and we tax tobacco to raise money for the government and to reduce smoking. And we tax alcohol, and we do it to raise money for the government and to reduce drinking. And then we tax your paycheck. You don't get as much for your work as you would because we tax your paycheck, and we do it to raise money for the government. And the answer would be, and reduce working, because it makes work less valuable, so you find other things to do with your time, or you barter, or you grow a garden, or what have you. And so the economists have said, suppose that we put a tax on carbon, and suppose we use that to reduce the tax on your paycheck. And the Congressional Budget Office looked at this a couple years ago, and they said, suppose for now we just ignore climate change. Everything he just said is an evil lie. There's nothing to worry about. Trading a carbon tax for a wage tax doesn't hurt the economy. It may even help a little bit. Now, you add in that you avoid climate change, and you end up with a bigger economy with a carbon tax than you do without it. The first time I testified to a Senate subcommittee, it was chaired by a Republican who wanted to put a price on carbon because that's the conservative thing to do. You don't have regulations, you have a price signal, you let the free market deal with it. And you will still find a lot of conservatives that like that. Now, be clear, it screws poor people because they spend more of their income on fuels than rich people do. If you have a car and you commute to work, you don't spend nearly as much as a billionaire with a yacht, but the billionaire with the yacht is buying a lot of art too, and as a fraction of their economy, it's smaller. So you might want to tweak it to help poor people in some fashion, but broadly, if you put a carbon tax in, you get the whole economy working to reduce it. You can do a carbon tax in ways that do not grow the government, that are not intrusive. In fact, getting rid of some wage tax and going to a carbon tax is less intrusive if you're a libertarian. We already have our fingers in gas and oil in various ways, and you quit looking as much at paychecks. Okay, how are we doing here? Who's next? Yes. Okay, we got one. Yeah.
I would like you to comment, if you would, on several other factors that you have not touched on yet. We have circumstances that are going on now, such as the defrosting of the taiga, that are going to accelerate this process, loss of ice sheets. Where's the point of diminishing return as far as being able to say, we can't stop this process anymore?
So you're certainly correct that when we make it warm, there's a lot of carbon frozen in cold places, you know. And if we thought the soils become more like warm places, that probably means carbon coming out. There's some carbon frozen in methane in the seafloor that probably comes out with warming. Whatever we do, nature is likely to amplify it. We are cautiously optimistic that that will be slow, and we're hopeful that it won't be too bad. The first degree, as I said, the first degree of warming is about free, but we've already used it. The second degree of warming is not all that expensive, but we're committed to it. The third degree of warming starts to get really expensive. The fourth is way more expensive than that, and so on. So whenever we decide to deal with it, we just avoided the worst. And I don't think, we're a weed. We humans are the best weed that ever was invented. We'll be here somewhere, somehow. But this is about how well we do. And the sooner we get started on it, the better. But I don't think we ever get to the point that we should just give up, sit down, and wait to die. I think we'll always be able to improve relative to doing nothing. And so I worry, and I work on abrupt climate changes. I work on tipping points. That's much of my career has been devoted to them. I'm really worried about some tipping points and ice sheets right now. And we're expecting, 3 feet of sea level rise at the end of the century, and it might be 2, and it might be 4, and it might be 15 or 20. And that distribution scares me. That distribution is sort of everything in this game. It could be a little better, it could be a little worse, it could be a lot worse. But in turn, that says there's more gain to be had if we're smart about it. So I think this is a challenge, but it's a challenge we can meet. So I'm still, I spent the day with your students here, and I'm still optimistic. And if I hadn't spent a lot of time with students, I'm not sure I would be. Yes, one. Yep. Okay. One in the middle here. Yep, we're getting there. Hey. All right. Great questions, by the way. Thank you. I'm sorry if I'm too long-winded in answering, but yes.
Okay, thank you. Everything in this country seems to come down to cost and price, and isn't there some evidence that wind energy already is cheaper and more profitable for the consumer, not necessarily utility? As an example, Texas that produces sometimes 45% of their energy in wind, and that solar is getting closer.
Yeah.
So isn't this a win-win that's really a win-win?
I believe you're completely correct. So I believe you've got it. Right now, adding a little bit of power to the grid in most places, wind seems to be the cheapest you can add. Sun is getting to be competitive. And that's if making it complete renewables, think 30 years, because we got some learning, we got some stability, the wind dies and the sun sets. But right now, adding a little bit more seems to be very inexpensive, and it seems to help in a lot of ways. When I started in this game, they used to tell us that we'd never get past 20% renewables without a lot of storage, and a bunch of places have gone right past 20% without a bit of a change. And so I think you're completely right on that. Let me show you something here, because you raised a point that I think is really important. And we talked about this with the students today, but I want to walk you through it again. There's a small number of plots up here. Over here is, if you go around and ask Americans, county by county, is the climate changing? Is there climate change? Blue would be no, and red would be yes. And so down blue is no climate change, red is yes, yes, of course there's climate change. What you'll notice is most Americans believe there's climate change, but not by much. Most of them, there's a whole bunch of them actually think global warming stopped in 1998. Now, if you ask, do humans cause it? Most Americans by county don't. We do, but they're confused about this. And you'll see a few oranges and yellows on there that believe humans are causing climate change, but a lot of those blues and grays, we're not doing it, okay? Do scientists agree on this? Right, orange is yes, scientists agree, blue is no, we don't. We do, very, very, very strongly. But notice that most Americans have been convinced that we don't. Is it bad? They're a little more worried, but still there's a similar pattern here. And now to your wind question. Even if it's not a problem and it's not bad, are there smart solutions? Whoa. Yes. And a whole lot of places that don't want to talk about climate change want to build wind because they think it's fantastic. And so this business of, yes, there are smart solutions, even if we're not that worried about it, we can do things that help us. And a lot of that is going to be your wind. But the last one, I was in a communications class first. This last one is you, okay? There are smart solutions. Are you talking about them? There are smart solutions. Are you talking about them? No. That's important. So thank you. That's a really good question. Yes. So how are we doing here? One up front? Sure. Yeah.
Following up on that a little bit, what about batteries?
Batteries.
Elon Musk is doing a fantastic job out there in Sparks.
Right.
Okay, but that seems to be the weak point in solar.
Right. So eventually, like I said, adding a little bit of wind and sun is actually really cheap now. Adding a huge amount becomes expensive, and for exactly your issue, is that we don't quite know how to build a fully integrated, sustainable 100% one. There are many paths to get there, and there are really serious people, good folks, Stanford, what have you, who have put together plans on how to get there, and some of them include your batteries. So in the short term, maybe one of the easiest things is actually gas. A coal plant has to put out power at some level. They can turn it down tomorrow, but they can't turn it down for an hour. They're just not designed that way. And so if the need for electricity varies, the coal plant can't follow it. A gas plant can. So if you built some gas with some gas turbines and then you just started building renewables like crazy, the gas can fill in until you get storage or other things. When you get to storage, integrating more, having wind and sun, pushing energy a little farther around helps smooth it out as well, because the wind doesn't die everywhere in the nation at the same time. Eventually, when it gets to batteries, it may be that we do utility scale batteries. It may be that we get smart. Suppose that people buy a lot of electric cars or plug-in hybrids or cross-fuel vehicles or something like that. And suppose we build an electric grid that is smart. And so the US military, Penn State, have vehicles. Maybe you have a vehicle. And when you park it, you plug it in. And you say, I'm ready to play now. And if the grid needs a little electricity, they buy it out of your battery. They don't drain it all the way, but they can buy some from you because you told them they can. And if the grid has some extra electricity, they give it to you and you store it. And they pay you a little bit for being their battery because you got a battery in your car, why not use it? And even a few % of the vehicles allow you to get an immense amount of renewables on the grid and still be stable because the storage is there. In the time we all turn over our vehicles, that's an immense number of batteries. When the battery is dead, it's still got half its life, and you take it out and you rack them up and you use them for a few years before you recycle them, and in 20 years there's batteries out the wazoo. So there are many possible ways to do this. Right now, one study said if we put batteries on the grid, it'll help coal and nuclear. That wind and sun don't really need them quite yet, but coal and nuclear do because they're so unadaptable. And maybe we're headed towards a grid that looks more like the internet. You can be a buyer, you can be a seller, you can be a user, you can do lots of things. It's highly adaptable, it's highly flexible. That is decades of learning. It is jobs for electrical engineers, it's jobs for bright people, but it's doable. Yeah, one in the middle back here. Yeah. Sorry. Oh, I'm sorry. Yeah, okay, so we'll get that one and then this one. Sorry, okay, yeah, sorry.
I was wondering if you have some figures on percentage of CO2 put out relating to fossil fuel usage versus the amount of CO2 that occurs naturally no matter what we do.
Right, so human emissions are about 100 times volcanic. So the CO2 comes out of volcanoes, we trade it back and forth between plants in the air and other things, and eventually it goes into breaking down rocks in chemistry, and we're about 100 times the natural. It might be 50, might be 200, but we're sort of 100 times the natural flux. So the rise in CO2 is us. A little bit of that is from cement making. A little bit of that is from deforestation. It is more from fossil fuels than anything else, and that will become bigger as we go forward. So thank you. Yeah, one was over here. Yeah.
Realizing you're a geologist, do you have any suggestions for how we talk to people who do not believe climate change is real?
Yeah. This is the hardest one, and we've been talking about it with students and profs all day. We haven't solved it. I've been doing this most of my life, and I haven't solved it. I wish I had an answer. This may be part of it. That there are people that are interested in the fact that there are jobs in this, there's money in this, there are ways forward in this. And so maybe you start on something that's renewable energy, it's a vision of a bright future, and then contrast that with the bad thing. I suspect that it's a lot of different ways for different people. I think there are people who really are worried that I'm lying about temperature data, but not very many. I think there's a lot of people worried about their job. I think there's a lot of people actually recognize that we owe a debt to the fossil fuels. And so finding the way one by one, when I get a chance and I'm not teaching students at home, I come and see you. And I do that because ultimately I think you're really important. And so I think it's going to take a lot of us to change this map to match this one. And if we were talking about it, I think we'd get there. Yeah. Oh, I'm sorry, there's one right behind you. Yeah, sorry.
So we talked about methane earlier, and I just have a two-part question. One, why do we seem to never really talk about animal agriculture? It seems to be an unknown topic in the role in environmental destruction. And the second part to that is, can you honestly call yourself an environmentalist if you eat meat?
Right, so it is very clear. I showed you these plots up there earlier. We used to, long ago, grow food that we ate and let animals go eat grass that we couldn't eat, and then we ate the animal, and that worked fine. And now you know, you wouldn't have asked this question if you didn't know, you know, that we take human food and we feed it to animals, and if they're chickens or turkeys, they burn half of it and make heat and turn half of it into food that we eat. And if they're beef, they burn 90% of it, and we only get 10% of it. And so we're taking food that could feed people and turning it into animals that are mostly feeding themselves, and then we eat what's left, and they belch and make methane, and we truck them around and we refrigerate them. And there's no question that the agricultural system, as it's configured, generates more greenhouse gases than it needs to. And on a hungry world, the question of whether this is a good thing is worth serious consideration. In the same sense, if you go down to the Texas ranchers and say, you know, how about a carbon tax? But you start the discussion with, how about getting off of your cheeseburger? The discussion ends right there often. And so the question of how to communicate this, there are people who believe deeply and passionately that we all need to get to vegetarian. I think virtually everyone, you get at some level, eating a little bit lower on beef, forgoing a cheeseburger a week probably helps the health as well as everything else, and it's good. If there were a carbon tax, in some sense, you'd see it show up because the price of beef would go way up relative to other things, and that would solve the problem. So, so there's lots of ways to look at this when this is a challenge for you as a communicator, as a passionate person. But it's very clear that if I were to lead with what we just said right here, there's a lot of people that would not follow. And if you say that, well, I'm hiding it, I'm going to take away your cheeseburger later, they will be really ticked off. And so finding the way to do this from an ethical standpoint, from a moral standpoint, from a health standpoint, is your challenge as a communicator. And I think that's accurate. Okay? Was one right? Yes.
So you mentioned renewables being a big part or most of the equation. How hopeful you are maybe conservation being part of that?
Yeah, conservation is fantastically important. And we went to the local people who are really good at this about 5 years ago and said, should we conserve, or should we re-insulate the house, or should we put solar panels on? And they said, re-insulate the house. And they put the solar panels on last week, so we've done both of them. But it's very, very clear that conservation is a really big piece of this. And we have seen recently that CO2 fossil fuel emissions have flattened while economic growth has continued. And that's a statement for conservation. That's a statement that we are actually making this pay. And that's a really good thing. I was out at Weber State in Utah. And they, right after the big crash, they went to their endowment and said, put your money into conservation and we'll pay you back. And we'll pay you back better than your investments are paying. And they did. And they're using the extra to do bike trails and things like that. But they said, invest in conservation here and we will make it pay. And they made it pay. Okay. So I think back here, I would guess we're getting towards the end here, but yeah, go ahead, please.
Is this on? Okay, good. So I'm somebody that happens to be really interested in tropical cyclones, and global warming is obviously a big thing, part of that. Over the past few months, I've been working with a little team, Forster team. I've been working with them, digging up some past history on tropical cyclones. Something that's been really interesting to me is that 4 out of the last 10 years have had worldwide, since 2010, 4 of the years have had the 10 lowest numbers of tropical cyclones worldwide. Meanwhile, of those since 2010, most of them have had shown above average, very strong tropical cyclones. And something that really intrigues me, and I'm wondering why this is exactly happening. Although sea surface temperatures are increasing, I would think that there would be more disturbances with more moisture and whatnot. Why is that trend happening, and is this trend likely to continue, and what would be the ramifications of these stronger systems?
Right, so thank you. Tropical cyclones, hurricanes, you know, hugely important in a bunch of different ways. If you think of them as a fire, they're not a fire, but think of it for a minute. A fire, you need a match, and you need something to burn, and then you need the right conditions. It can't be raining on it or something like that. Tropical cyclone, you know, you need the fire, the stuff to burn is warm water. It's the energy source. So you can get energy out of the warm water. You need a match, like a thunderstorm coming off of Africa into the Atlantic formation zone. And you need the right situation. You can't have too much wind shear, you blow the top off. And what seems to be coming out is a very tenuous conclusion that we will actually see fewer tropical cyclones in a warming world because of lack of matches or because of bad conditions, and especially wind shear. But the ones that get big will get bigger because there's more fuel, and when the conditions are right, they'll burn like crazy. And so the suggestion is that because of some combination of loss of the triggers and wind shear, that fewer cyclones, but the biggest ones get bigger. The damage is almost all caused by the biggest ones. So this is making really destructive things farther apart so we sort of forget about them and then get hammered is sort of the worst thing to do. How are we doing? Some way in the back here? Yeah.
So fairly recently, the Bulletin of Atomic Scientists adjusted the doomsday clock to 2.5 minutes to midnight. Part of their decision to do this was their initial inclusion of climate change into their modeling that they use, both that and recent comments by the President of the United States regarding climate change. Do you believe, in your professional opinion, that climate change is as big of a risk to humanity as nuclear fallout?
Yeah, I'm not sure it's entirely fair to separate them. So the question might be, under what circumstances would we drop bombs on each other? And the answer is when we're really ticked off at each other. And then the question is, in a world where it's getting harder to feed your people, are you more likely to get ticked off at people? There's a lot of worry in the intelligence community about the fact that Asia's big rivers are getting dammed for hydropower with a lot of hungry people downstream, and that some of the dams on some of Asia's big rivers involve countries that have bombs. And so there's a question whether these are really separate issues. It is possible that people get mad at each other and drop bombs without climate change, but if we stress people by climate change, we may make the bombs more likely. And so I'm not sure that we can say, is one worse than the other? They may be different faces of a bigger problem. Yeah, how we doing? Yep. Not at the moment. Sure. Thank you. Who's got the last one? Come on, one big one. Here we go. All right. Yes, one right down front here, please. So can we, yep. Here we go. This has been fun, by the way. Fantastic questions, and thank you.
This is a micro-level question. What can we do on the individual level?
Yes, thank you. That is such a macro-level question. That is the question. I did not plant her, honest to goodness. This is brilliant. Thank you. So this is one of them. People believe there are solutions, and they're not talking about it, right? So that's one of them, is you vote, you talk to people. And then what I like to say is you can't solve it. No matter how good you are, no matter how hard you work, you can't solve it. We can. But you can't. But pick something. And what we know is there's this big hump that life is difficult while we learn a new way, and then we end up on the other side with something that's better. And we know we can build a better world this way, but getting there is hard. And if you pick something to help, and whether it's bike trails or whether it's recycling or whether it's gathering food and taking it that would be thrown away and taking it to poor people who want to eat, whether it's putting the solar cells on your roof, whether it's whatever, pick something. And if everybody picked something, we get there. And so I think you do the macro level thing. You talk, you vote, you bring the information to people in a respectful way that helps them, and I'm sure you do. And then find something that you believe in if you want, and push that one. And it may be doing your job. You're a student, and you get the new job, and you're in business. And you get in, and you work for a year, and then you say, there's a market here of people who want to do the right thing, and we can make money, and we can make the planet better, and I know how to do it for you. And it may be doing your job, but doing your job in a way that moves us in the right direction. And it may be becoming an engineer or a scientist or an inventor and inventing the thing. It may be building the grid, but it may just be helping your faith community. It may be, pick something. And if all the good people pick something, we get there. And we win, and the future is brilliant. And the students of Lycoming College are going to continue to contribute to this. And I thank you for inviting me. We thought relativity and quantum were the craziest things in the world. You've got them in your pocket. And if you didn't have them in your pocket, you wouldn't have a cell phone. And be very clear. If you took the sand and the oil and the rocks and you took them down to the Senate and you gave them to the senators and said, please turn this into a cell phone, the monkeys would type Shakespeare before we'd have a cell phone. Right? But science put it in your pocket, and it really does work. And science does advance. You'll meet the Galileo people. Galileo changed somebody's mind, and then people didn't like Galileo, so you scientists will change your mind, and we don't have to worry about global warming because you always change your mind. No, we don't. Right? It is true that for little things, we needed quantum mechanics and that Newton wasn't right. And it is true for really big, fast things, we needed relativity and that Newton wasn't right. We needed Einstein and Bohr. But when I model a glacier, I don't write a quantum wave function and I don't use a relativistic calculation, I use Newton. And the useful parts of science, the big things, I don't think we've ever thrown one away. At the point we have something that works, when we get new discoveries, they build on it. They don't overturn it. Science works and it builds, and I think that's really important to know, okay? Now, this is the energy group. We're talking energy. I'm going to lean on energy a lot here. I don't know exactly the wattage of that bulb, but it's probably 100 watts. The wattage of me is 100 watts. I put out if you could collect the energy coming off of me right now, I'm about one light bulb. And you're one light bulb, and you're one light bulb, and you're one light bulb. We get that by burning food, and our food use is about 2,000 calories per person per day. I ate the moose at dinner, and I may be over 2,000. But at any rate, 2,000 calories a day is 100 watts burning day and night. But I ride my bicycle at home a lot, but I took a car over here. And the moose was refrigerated, and I didn't refrigerate it, and I'm not riding a bicycle to power the light. And if you take all the energy that is used to take care of me, and you put it in these units, it's a little over 200,000 calories a day. What I can do is 2,000. What is done for me is 200,000. What is done for you is 200,000, and what is done for you is 200,000. And it's 80-some% fossil fuel. And it does the transportation and the heating and the cooling and the plowing, and we love it. Be very, very clear. It's fantastic, and we don't want to give this up for anything. When I came over this morning, I drove by the iron furnace. I come from the town of State College. The town of State College is a suburb of Penn State. When Penn State was founded, there was no State College. It grew up to serve the university. Penn State was founded up the hill from the iron furnace. And when the iron furnace was working, it would have looked like this. This is Hopewell furnace in a diagram from the Park Service, but it was turning red dirt and limestone flux into the iron that built the East. And the power to make that rock melt came from charcoal. And the charcoal came from trees. And it came from lots of trees. And if you did this very long, it did that to the landscape. A furnace in blast And the people taking care of it took the trees from about a square mile a year. And then they had to wait 30, 40, 50 years for more trees to grow back. So a furnace, when it was running, a square mile of trees a year. Now, if you go to a gazetteer of Pennsylvania, go to the map and say, in Pennsylvania, so I'm going to take you on a tour. I'm going to start off, so that's an iceberg. I wanted to thank Barb Eldred at the Dean's office who has arranged all of this stuff, and she jumped through a lot of hoops. And thank you for coming out tonight. And I'm going to scare you a little bit, I think, before I get to the good news. And I'm going to do the scaring with penguins to make it look a little better. So these are pictures I took in Antarctica at some time or another. So we're going to use penguins to smooth it off. And I'm going to walk you through a few points. And this first one I probably shouldn't have to do, but I'm going to do it anyway because we need to carry this out of here to other people, how fantastically useful science is. Then I'm going to walk through how we really get help from energy. And we owe a lot to fossil fuels, but it's going to end. We have to do something else, and the sooner we get started on doing something else, the better we are. So that's where we're going in the course of today. So we'll see what we can do to this, okay? So, like I say, I don't think I would have needed this, but I suspect that now I do. That it is worthful remembering that science works, that medicines do cure diseases, that people take computers and they design new airplanes and then they build them and then they take them out on the runway and they fly. And, you know, this is something else. And, you know, I have my cell phone in my pocket. You probably have one too. And it is... Think about it for a minute. How would you make a cell phone? Right, it's a little bit of sand for the glass and the silicon, and it's a little bit of oil or some organic material for the plastic, and it's the right rocks, the ones with the rare earth elements and the gold and the copper, and science and engineering. And I've got Einstein in my pocket. Right? The GPS uses relativity, it uses special and general relativity, and if we didn't understand relativity, it wouldn't work. And it uses quantum mechanics in the computer. When I was a student, be perfectly honest, do we remember the name furnace? All of the ones on the left there are furnaces, and there's a whole bunch more that aren't on that list. And every one of those in blast is a square mile of trees a year. Now, the ones on the right are forges. You took the pig iron and you forged it into useful things, Valley Forge, and another square mile of trees a year. That and a whole bunch more did that. We are in Penn's Woods. We are in Pennsylvania. When the first European settlers came here, they said that a squirrel could go up a tree on the Atlantic coast and stay in the trees to the Mississippi. The first forester of the Commonwealth was Rothrock, and Rothrock wrote about the Pennsylvania desert. Now, it wasn't a desert, it still rained, but we didn't have trees. We have 1 million deer in Pennsylvania, they were essentially gone. We have elk in Pennsylvania because we re-imported them from the Rocky Mountains, they were gone. I'm a Nittany lion. There's no Nittany lions. There wasn't a deer to eat, and there wasn't a tree to do it behind. Basically, if it was bigger than a rabbit or a squirrel, we chased it out of the Commonwealth. And we didn't let the trees grow back until the 1900s. Now, if you've ever tried to read by firelight or by candlelight, it's not very easy. And so what did we do for lamps? And the poor people used to use a biofuel called camphene. It burned clean. It was alcohol and turpentine, but it was sort of explosive. And there are horrible old stories in the newspapers of people burning themselves to death. And the rich people burned whales. So you send Yankee whalers out to scour the world oceans and to find whales and to cook them. and then to bring back the oil, and then you can burn it. And this is the history of whale oil production in the Yankee fleet. The date is 1800 on your left, it's 1880 on the right. You can see peak whale oil.
Good evening. My name is Julie Burns, and I'm a senior biology student here at Lycoming College. And I'm very excited to be introducing tonight's guest speaker. But I'd first like to start by thanking our sponsors for the event. They are Lycoming Center for Energy in the Future, which takes an interdisciplinary approach to studying how we use our energy and the effects this will bring in the coming years, as well as our outdoor leadership and education program, which helps to develop leadership skills and learning beyond the traditional walls of the classroom. Our Sustainability Committee, which is a student-led organization dedicated to bringing sustainable initiatives to campus. And finally, our Clean Water Institute, where research students help to expand our knowledge and restore the waterways along the West Branch of the Susquehanna River. So our guest speaker tonight is the Evan Pugh Professor of Geosciences and Associate of the Earth and Environmental Systems Institute at Penn State University. He has served on many advisory panels, such as the National Research Council's panel on abrupt climate change and the United Nations Intergovernmental Panel on Climate Change. He was the co-recipient of the 2007 Nobel Peace Prize and has written numerous papers and books, one of which was chosen as Science Book of the Year by Phi Beta Kappa in 2001. Currently, he teaches and conducts research on climatic records and flow behavior of large ice sheets in order to predict changes to sea levels and climate in the future. So please join me in welcoming Dr. Richard Alley.
Thank you. Oh, dear. Oh, what a pleasure. Thank you. Thank you. It is really fun. I have had a day. I got up at 6 this morning and got a fleet services car and drove over here, and we've been going since 8. And I've been to a bunch of classes. This is a fantastic place. And the students and the faculty are really doing wonderful things, and it is an honor and a privilege to be here. If you're sitting way back in the back corner and you have trouble seeing the screen, the slides are over here, and there are seats up front. So if you have trouble seeing, come on over, and we're friendly. We don't bite. So